Based on analysis of observational data and expert commentary from multiple defense and aviation analysis outlets, the Developmental Combat Aircraft Program, unofficially designated as the J-36, has progressed to a significant new phase with the confirmation of a second flying prototype. This new airframe, observed approximately 10 months after the initial prototype's flights began, exhibits a comprehensive series of structural and aerodynamic modifications that provide substantial insight into the program's development philosophy, technical challenges, and intended performance characteristics. The scale and nature of these revisions indicate a highly iterative and dynamic development process where empirical data from the initial flight test campaign is being rapidly incorporated into the airframe's design. The most visually prominent and technically significant modifications are concentrated in three primary areas: the propulsion and exhaust system, the air intake configuration, and the landing gear structure. Each of these areas represents a critical subsystem where design choices directly conflict with one another, requiring engineers to make calculated trade-offs between competing priorities such as stealth, aerodynamic performance, weight, and mechanical complexity. The propulsion system's exhaust configuration has undergone a fundamental redesign. The first prototype featured a deeply recessed exhaust system where the engine nozzles were set forward from the aircraft's trailing edge, shrouded by the rear fuselage structure. This design approach, reminiscent of historical stealth aircraft concepts, prioritized the reduction of the aircraft's infrared signature and radar cross-section from the critical rear aspect by physically shielding the hot, radar-reflective engine turbines and nozzle actuators. The second prototype has completely abandoned this configuration in favor of exhaust nozzles that are now positioned flush with the trailing edge of the airframe. These new nozzles feature a starkly angular, two-dimensional geometry with serrated edges. The specific shape and placement are consistent with known designs for two-dimensional thrust vectoring nozzles, which use moving panels to deflect the engine's exhaust stream. This modification strongly suggests a recalibration of the design priorities, where a degree of rear aspect stealth may have been traded for a substantial gain in flight performance and control authority. Thrust vectoring provides powerful control moments that are independent of aerodynamic forces, which is particularly critical for a tailless aircraft design that lacks the conventional vertical and horizontal stabilizers used for stability and control. This enhancement would expand the flight envelope, improve high angle of attack maneuverability, and potentially compensate for inherent instability in the tailless configuration, especially at low speeds or high altitudes where traditional control surfaces are less effective. Concurrently, the air intake system has been systematically revised. The initial prototype employed a mixed intake configuration, featuring a dorsal diverterless supersonic intake (DSI), a bulged, bump-like structure, combined with two lower side-mounted trapezoidal, carrot-style intakes that included boundary layer diversion splits. The second prototype appears to have standardized its intake design, replacing the two lower trapezoidal intakes with additional DSI units. The DSI design is a modern aerodynamic solution that uses a precisely shaped compression bump to divert the slow-moving boundary layer air away from the intake, eliminating the need for the complex mechanical racks, gaps, and bleed air ducts found in traditional diverters. This results in a simpler, lighter, and more reliable intake structure. From a signature management perspective, the DSI's smooth, continuous contours without gaps or moving parts are more effective at reducing radar cross-section, particularly from frontal and side aspects. The forward-swept lower lip on these new intakes is another design cue associated with optimizing airflow and radar wave deflection at high angles of attack. A third major area of revision, which points to a fundamental reassessment of the aircraft's weight and internal layout, is the complete redesign of the main landing gear. The first prototype was equipped with a tandem two-wheel main gear, a configuration typically reserved for the heaviest classes of aircraft, such as strategic bombers, as it concentrates immense load along the fuselage's centerline. The second prototype has transitioned to a more conventional side-by-side twin-wheel truck arrangement. This is not a minor adjustment but a profound structural change that implies a significant re-engineering of the airframe's internal support structure, the wing box, and the gear bay itself. The reasons for such a change could be multifactorial. It may indicate a revision of the aircraft's maximum gross weight, a redistribution of internal mass such as fuel tanks or weapons bays, or a decision to accommodate different operational requirements, such as runway strength. The side-by-side configuration often allows for a wider stance, which can improve ground handling, and may also free up internal volume along the centerline for other systems. The emergence of this extensively revised second prototype within a short timeframe is a strong indicator of the program's development tempo and methodology. The first prototype likely served as a proof of concept and systems integration testbed, focused on validating the basic flightworthiness of the radical tailless, three-engine design and gathering baseline data on its handling, performance, and subsystems operation. The extensive, cross-system modifications seen on the second airframe are characteristic of a program that is proactively and rapidly incorporating lessons learned from its initial flight test campaign. This iterative build-test refine cycle is a core principle of modern aircraft development, but the scale and speed of these visible changes are notable. They suggest a development philosophy that prioritizes achieving a capable and optimized final product through successive prototypes, rather than freezing the design early. This process allows engineers to de-risk the program by identifying and solving fundamental aerodynamic and structural challenges before committing to a production configuration. The progression from the first to the second prototype demonstrates a clear trajectory toward refining the aircraft's performance, manufacturability, and ultimately, its capability to meet the specific operational requirements for which it is being designed.